Welcome back to our Azure Kubernetes Service Networking Masterclass. In Episode 1, we built the foundation. We learned how Kubernetes networking works, why Azure CNI matters, how pod communication happens, and why technologies like Cilium are becoming the future of cloud-native networking. At the end of that episode, we had a fully functioning AKS environment. Pods could communicate. Services could discover each other. Network policies were protecting workloads. Everything inside the cluster was working. But we had one major problem. Nobody could access the application. Imagine our digital banking platform is now live. The development team has deployed internet banking. The payment APIs are healthy. The fraud detection engine is running. Customer onboarding services are operational. But when a customer opens their browser and types the banking website address, nothing happens. The application exists. The infrastructure exists. The services exist. But there is no controlled pathway allowing traffic to enter the cluster. This is where ingress architecture begins. Today's episode is about understanding how traffic enters Azure Kubernetes service. We are going to follow a real customer request from a web browser all the way into a Kubernetes pod. And along the journey, we'll understand load balancers, services, ingress, nginx, application gateway, application routing, custom domains, SSL, private DNS, and modern production traffic management patterns. Let's begin by understanding one of the most confused concepts in Kubernetes: ingress and egress. Engineers constantly mix these terms together. The easiest way to remember them is this. Ingress means traffic entering the cluster. Egress means traffic leaving the cluster. Think about an airport. Passengers arriving at the airport represent ingress. Passengers departing from the airport represent egress. Today we focus entirely on ingress. How users enter the platform. We'll cover egress in detail during Episode 3. Now let's follow our customer. A customer sitting at home opens a browser and types onlinebanking.contosobank.com. Immediately several network services begin working together. The browser needs an IP address. The operating system performs a DNS lookup. DNS responds with an IP address. The browser then attempts to establish a secure connection. Traffic reaches Azure. Azure then forwards traffic toward our AKS environment. Finally, Kubernetes routes traffic to the correct application. This entire journey may happen within milliseconds. But there are many architectural components involved. Understanding each one is critical. Let's start with Kubernetes services. Many engineers believe the first networking component users interact with is ingress. That's actually not true. The first fundamental building block is a service. Remember from Episode 1 that pods are temporary. Pods can disappear. Pods can move between nodes. Pods can scale dynamically. Applications need a stable endpoint. Services solve this problem. A service creates a stable virtual endpoint in front of pods. Kubernetes provides several service types. Cluster IP, node port, load balancer, an external name. Let's understand each one. Cluster IP is the default service type. It creates an internal virtual IP that exists only within the cluster. Suppose the payment microservice must communicate with the authentication service. The payment application does not need to know which authentication pod currently exists. Instead, it talks to the authentication service. The service handles everything else. This creates stability and abstraction. Next comes node port. Node port exposes a port on every Kubernetes node. Traffic can arrive at any node using that specific port number. Historically, node port was frequently used as part of ingress architectures. Today, it is more commonly used as a building block underneath other solutions. Then we have load balancer services. This is where Azure becomes extremely interesting. When you create a service of type load balancer, Azure automatically provisions an Azure load balancer resource and connects it to your application workloads. /learn.microsoft.com/en-us/us/us/us/en-us/forward/learn.microsoft.com/. https://learn.microsoft.com/en-us/forward/aks/concepts-network. This is one of Kubernetes' most powerful capabilities. Infrastructure is automatically created from application definitions. The fourth option is external name. This allows a Kubernetes service to map to an external DNS name. Applications can use familiar service names while accessing resources outside the cluster. /learn.microsoft.com/ https://learn.microsoft.com/en-us/forward/aks/concepts-network-services. Now that we understand services, let's discuss load balancing. Load balancing exists because modern applications rarely run on a single instance. Imagine our banking login service. During business hours, tens of thousands of customers may attempt to sign in. A single pod would quickly become overloaded. Instead, Kubernetes runs multiple replicas. The challenge becomes distributing traffic evenly across those replicas. This is where load balancing enters the architecture. There are two major types of load balancing we must understand: Layer 4 load balancing and Layer 7 load balancing. Layer 4 works primarily with IP addresses and ports. Layer 7 understands application-level protocols, such as Hypertext Transfer Protocol. An Azure load balancer is primarily a Layer 4 service. It can distribute traffic across nodes efficiently. However, it doesn't understand sophisticated application routing decisions. Let's consider a practical example. Suppose our banking platform hosts the following applications: online banking, loan applications, investment management, insurance services, customer support portals. All of them share the same public IP address. How do we decide which request belongs to which application? This is where ingress becomes necessary. An ingress acts as the intelligent traffic manager for Kubernetes. Rather than simply forwarding packets, ingress understands website requests. It understands URLs. It understands host names. It understands secure sockets layer termination. It understands application routing. An ingress resource allows us to define rules. Requests for accounts.bank.com go to the account service. Requests for loans.bank.com go to the loan application service. Requests for support.bank.com go to the customer support application. This creates enormous flexibility. And it dramatically simplifies application exposure. However, there is an important detail. Ingress itself is merely a set of rules. Something must enforce those rules. That something is called an ingress controller. An ingress controller reads ingress definitions and performs the actual traffic routing. One of the most popular ingress controllers in Kubernetes history has been Nginx. Let's discuss why. Nginx became successful because it is reliable, flexible, powerful, and relatively easy to deploy. It can route traffic, terminate SSL connections, perform path-based routing, perform host-based routing, apply security policies, provide observability, support advanced configuration scenarios. For years, Nginx became the default ingress solution across much of the Kubernetes ecosystem. If traffic entered Kubernetes, there was a high probability Nginx was involved somewhere. Let's follow our banking application architecture. Traffic arrives from the internet. An Azure load balancer receives traffic. Traffic reaches the Nginx controller. The Nginx controller evaluates ingress rules. Traffic gets routed to a Kubernetes service. The service forwards the request to a healthy pod. The customer receives a response. While this architecture is extremely common, it creates operational responsibilities. Someone must manage Nginx. Someone must upgrade it. Someone must patch vulnerabilities. Someone must monitor performance. Someone must troubleshoot incidents. As Kubernetes matured, many organizations wanted a more managed experience. This requirement led to application routing solutions. Application routing simplifies ingress management by automating controller deployment, DNS integration, and route configuration. Instead of manually assembling components, teams receive a more integrated experience. This is particularly attractive for platform teams that manage many application teams. The less infrastructure developers need to manage, the faster innovation can occur. Now let's discuss one of the most important enterprise components in Azure networking: Application Gateway. If Nginx is a highly capable software traffic manager, Application Gateway is an Azure native application delivery platform. To understand why many enterprises choose Application Gateway, we must first understand enterprise security requirements. Imagine our banking platform. Every request entering the environment may contain sensitive customer information. Login credentials, financial data, personal information, transaction requests. Security teams want protection before traffic reaches Kubernetes. They want inspection. They want threat detection. They want centralized governance. This is where Application Gateway becomes extremely valuable. Application Gateway provides Layer 7 traffic management at the Azure platform level. It supports advanced routing, SSL offloading, URL routing, session affinity, health monitoring, and perhaps most importantly, integration with web application firewall capabilities. Think of Application Gateway as a security guard standing outside the bank building. Requests are inspected before entering the internal environment. Suspicious traffic can be blocked. Known attack patterns can be identified. Security policies can be enforced consistently. In many regulated industries, this architecture becomes extremely attractive. Now let's compare Application Gateway and Nginx. Many engineers ask which one is better. The answer depends entirely on requirements. Nginx offers tremendous flexibility. Application Gateway offers strong Azure native integration and security controls. Neither is universally superior. Each solves different problems. Experienced architects focus on requirements rather than technology preferences. Now let's talk about application domains. Imagine our banking platform launches 3 services: online banking, mortgage processing, small business lending. Customers require user-friendly addresses. Nobody wants to memorize IP addresses. Humans prefer names. DNS solves this problem. The domain name system translates human-friendly names into IP addresses. Without DNS, modern internet applications would be impossible. Custom domains become especially important for branding and customer trust. A customer expects to see a banking organization's domain name, not a random cloud-generated address. When custom domains are integrated into AKS architectures, DNS records ultimately direct users toward load balancers, application gateways, or ingress endpoints. However, another challenge appears. Security. Customers entering banking credentials need assurance that communication is encrypted. This leads us to SSL and TLS. Although many people still use the term SSL, modern environments primarily use transport layer security. The objective remains the same. Encrypt communication. Protect data confidentiality. Verify server identity. Ensure trust. Let's follow a secure banking request. The customer opens the banking website. The browser requests a certificate. The server presents a certificate. The browser validates trust. An encrypted session is established. Only then does sensitive communication begin. This process happens so quickly that most users never notice it. Yet it is one of the most important security mechanisms on the Internet. Managing certificates becomes a life cycle challenge. Certificates expire. Certificates require renewal. Certificates must be stored securely. Private keys must be protected. This is why many organizations integrate certificate management with centralized security platforms and governance processes. Now let's discuss an area frequently misunderstood by architects. Private DNS. Everything we've discussed so far has focused on public user access. But many services should never be publicly accessible. Consider our fraud detection platform. Would customers access it directly? Probably not. Would regulators access it directly? Probably not. Would internal systems access it? Absolutely. Private DNS enables internal service discovery without exposing resources to the public Internet. Imagine a private banking platform. Internal applications communicate using friendly names. Private DNS resolves those names internally. External users cannot see them. This becomes especially important in private AKS clusters. A private cluster removes public access to cluster management endpoints. Administrators connect through private networking. Application communication remains internal. Enterprise environments often combine private DNS with hub-and-spoke networking architectures. The central networking environment hosts shared services. DNS services. Security controls. Connectivity platforms. Multiple AKS clusters consume those shared resources. This approach improves governance and consistency. Now let's put everything together. A customer opens a browser. DNS resolves the domain. The browser establishes a TLS session. Traffic reaches application gateway, or a load balancer. An ingress controller evaluates routing rules. Traffic reaches the appropriate Kubernetes service. The service forwards requests to healthy application pods. The application processes the request. The response travels back through the entire chain. What feels like a simple web page request actually depends on dozens of networking decisions working perfectly together. Before we conclude, let me share several trade secrets used by experienced AKS architects. First, keep ingress architecture simple. Complex routing rules eventually become operational headaches. Second, terminate TLS as close to the application boundary as practical. Third, treat DNS as mission-critical infrastructure. Many outages are actually DNS issues disguised as application failures. Fourth, separate infrastructure concerns from application concerns. Application teams should focus on applications. Platform teams should focus on networking and operational consistency. Fifth, always implement observability across every traffic layer. If you cannot trace a request end-to-end, troubleshooting will eventually become painful. And finally, never design ingress solely for today's requirements. Traffic growth tends to surprise everyone. Design for future scale, not current demand. Our banking platform now has a professional ingress architecture. Customers can access websites safely. DNS works correctly. SSL protects communication. Application Gateway or Nginx routes traffic intelligently. Private DNS enables internal communication. Routing is controlled. Security is enforced. The front door of our platform is now complete. But another major challenge still exists. Our applications need to call external systems, payment processors, identity providers, credit bureaus, fraud intelligence feeds, regulatory services, cloud ARPAs. How should traffic leave the cluster? How do we control outbound connectivity? How do NAT gateway, static egress gateway, HTTP proxy, instance-level public IPS, and outbound security architectures fit together? That is exactly where Episode 3 begins. In our next episode, we will follow traffic leaving Azure Kubernetes service and dive deep into egress design, outbound security, network fault tolerance, TCP keep alive, advanced connectivity models, and the enterprise networking patterns that separate lab environments from production-grade cloud platforms. Because in cloud-native architecture, securely entering the platform is only half the story. Securely leaving it is just as important.